Okay, any other question? If not, maybe we can start. So little phi is defined on a constant polynomial. Yeah. So we treat the constant in the polynomial ring as a constant polynomial. So constant and constant polynomial is almost equivalent. It's equivalent. Yeah. Does it make sense? Yeah. Is it okay we go on, or do you guys still want to stay on this substitution principle? Okay. Ziqian say go on. So Ziqian want to go where? Any suggestion? No idea. How about the rest?
Sir,
Yes.
can you talk about a little bit about the permutation representation, because that is quite confused. I don't know how the homomorphism go to like the groups homomorphic to the permutation S.
The group homomorphic to the permutation X.
The faithful representation.
Faithful representation. Wait, let me see.
Lecture 19 and 20.
So 19 and 20, yeah. So you're referring to which part?
The permutation representation.
Permutation representation. You mean this definition here? This one?
Yeah.
So what do you want to ask about? The definition, or can you repeat your question on this? Hello?
Let me think. What should
Yeah.
Is it this is the K followed by the Cayley's theorem? All group can isomorphic to the permutation.
It is related. It is related because when we prove Cayley's theorem, we let the finite group to act on itself. So there's a group action of G on G itself. Do you get what I say?
Hmm.
In the Cayley theorem, actually, we uses a group action. But that time, we didn't have a group action language. We just define some left representation map, left regular map. Actually, that map is a group action by G on itself. So to have a group action, you need a group and a set. But in this case, the group is G, the set is also G itself. So a group acting on itself. Does it make sense or not?
Okay, makes sense.
Yeah.
Okay, so the corollary below that group action of G on S is bijective correspondence to the homomorphic G2 permutation S.
Yeah.
Can you explain a little bit about this? Like,
How the bijection going on?
yeah.
Okay. Sure. So let me see. Okay. Okay, so the statement here is you give you a set, I give you a group. Okay. You can have a group action on the set X, no matter what is inside your set. The claim is give you this group action. It is bijective, corresponds to a homomorphism from G to the permutation representation of X. So meaning what? Meaning I give you a group action. Okay. I need to produce you a homomorphism. Okay, phi from G to permutation of X. Okay, so I give you an action, you need to give me a map. So to understand how to even build this map, it is crucial to know that what's the elements that you are trying to map between, right? Okay, so what is group action? Group action is a map from gx, g comma x to gx. For every g in G and for every X in X. So for every G in G and for every X in X, I need to tell you what is GX. Such that two condition hold, right? What are the two condition? Identity of G acting on X must give you back X. And then the product of G acting on X is equivalent to you act G2 first and then act by G1. So meaning if you want to check a group action, you just need to know where your generator, how the generators of the group act on X. Okay. Okay, so given this group action here, how do you produce a map, a homomorphism from a group G to permutation of X? So what is homomorphism from G to permutation of X? If I'm gonna define this map here, meaning given a group element, you need to send it to a perm X. So what's perm X? So let's recall the definition. What's perm X? What is perm X? Did I write perm X anyway or not? Okay, so perm X is here. We get the group perm X of permutation of X. So this is simply permutation of the finite group. What is the definition of permutation again? What are permutation? What's the definition of permutation? Do you remember? What are the map that are called permutation? Yes. So you say bijective map. So these are just bijective map. So how on earth are you gonna make this bijective map here? Give you a G and then make a bijective map. Actually, there's a natural candidate here. Which is this which is coming from this group action here. And we usually call this map MG on X. Okay, so we will send G to this MG here. So MG should be a bijective map from X to itself. Yes, Wang also say bijective map from X to itself. Okay, so how is this map MG defined? So I'll give you an X, and I give you MGX. First of all, you need to already start checking, does this MG form a bijective map or not? Aaron, do you think this is a bijective map or not, this MG?
Actually, I have a question.
Yes.
Since S is the set, right?
Yeah.
So is it the map is the set map to itself?
Yeah. Perm X is
So
a map from X to itself. Yeah. And then
um,
yeah. So my question to you is this MG bijective or not?
I think yes, because
Why?
it map to itself.
No, not every map to itself is bijective. But this map MG is bijective. Why?
Invertible.
It's invertible. Well, what's the inverse of MG? What's the inverse for MG? Anyone know what's the inverse for MG? Take the inverse element. Since MG inverse is the inverse of MG. You need to check. Right, you need to check. So what is MG inverse on X? What is MG inverse MG on X? Right. So in both cases, you will get like G on G inverse on X for the first one. For the second one, you get G inverse on G on X, which you will get X by the first group action if you compose G and G inverse together. If you want a longer step, you can invoke your group action property, right? And then you invoke group properties. So MG and M composed with NG inverse equals to MG inverse composed with NG equals to the identity map. Okay, so we have the right element in perm X. Then we still need to show that actually what we gave is a homomorphism, right? So you need to show that actually this phi here is a homomorphism, meaning you need to check that phi of G1, G2 equals to phi G1 and phi G2. Meaning you need to check what? M G1 G2 equals to M G1 composed with M G2. But M G1 G2 equals to M G1 G2. This is true by group action axiom number 2. Okay. Any question or not from Kyron again?
No question, I understand.
You understand? Okay. How about the rest?
Sir.
Yeah.
So we can say that this homomorphism from the permutation representation is we can say that the group action is faithful if every G act differently on S. Is that?
Yeah, that's true because the group action is faithful if the if okay, so what is it about this? Yeah, so you're talking about this. So the group action is faithful if the corresponding permutation representation is injective. So meaning the kernel is identity. So meaning for different GI, they have to act differently. Yeah. If they act the same, then you can take G1, G2 inverse, for example, but they are different, so they cannot compose to identity. So you have some non-zero identity element that act as identity. Yeah. Does it make sense or not? Why?
Yes, yes.
Yeah, yeah. How about the others?
Sir.
Yeah.
Can you go back to just now the discussion about substitution principle?
Substitution principle. Okay. Yeah.
Yeah. Just now we discussed that the kernel is x minus a, but
Yeah.
I think it is only work for when the substitution is happen in the polynomial is have the ring which equal to the ring it is mapped to.
Let me think. So what are you
because
saying?
because alpha is live in R prime.
Okay, so you mean let me think what are you saying about oh, you mean okay, so you mean alpha might not be in R, is it?
Yeah. Because alpha is live in R prime.
Yeah. Yeah, I think it makes sense. Yeah. Yeah. So if alpha live in R, then this is true. And then same for the next one also. You need to make sure your alpha I is in R also. I mean, not. Let me think. I think it is okay if it is living in Rx, the whole Rx. Because why we want this to be true? Because the kernel of phi should be living in Rx. Yeah, thank you, Wang. Yeah. Yeah, before you write down the kernel, make sure that it is living in the right ring. Yeah, okay. Thank you, Wayne. Got any other question or not?
Focus of exam.
Sorry? Focus
The
of exam.
focus. Yeah.
Should we discuss yeah. So you have a faithful is actually like injective, yeah. So group group action being faithful is the injectivity of the permutation representation. So group action is a map from a product to a set. So we don't quite talk about homomorphism there, but we can talk about homomorphism of the corresponding permutation representation. And then we can talk about injective there. Yeah. Does it make sense or not, Sui? Yeah. Or in other words, if you do your assignment, there's a statement says that if so gx equals to x if and only if g equals to the identity, then the group action is faithful. But we cannot say injective group action because if you want to talk about group action being a map, it is a double input map. So identity only exists on one of the component. The other component you still run through all the set element. So we cannot quite say injective group action. But we can talk about injectivity of a group homomorphism. Okay. Do you guys want to talk about assignment first, or you want to instead of talking about the focus of the exam, I will run through the main point in our lecture, which is important for the exam, and I'll do some contrast between group theory and ring theory. So do you want to see the compare and contrast first, or you want to discuss assignment first? Compare, okay. Okay, let's run through a big picture. So now is really a big picture. You want to see? Hopefully will help you to consolidate your knowledge. So basically, what we have done groups theory and rings theory. Okay, so actually there's a lot of similarity between them, right? So before even we talk about what is in the theory. So make sure we have the same we are on the same page, that we know the definition for both. So what's a groups? So a groups is basically a set, right? So a set with LOC, law of composition. Usually we call it multiplication. So we will put a cross here. Right. So how should this LOC be? So first of all, it has to be associative. And then it must have a identity, which usually we call a group identity. And inverses must exist for all elements. Sometimes you met a good groups, although this one is optional, where this LLC is commutative. You can imagine integer, right? And in this case, we will call it a abelian group. So abelian group, this Abel is coming from the Abel Price mathematician. Okay, how about rings? Rings is also a set. So we are playing with things, so they form a set. Rings has more structure. It has two LLC. One of them we call it addition, the other we call multiplication. You already seen from the assignment 4 that this multiplication and addition could be really different from what you know from the usual addition and multiplication. But that's to satisfy some property. Okay. Under addition, my set must be an abelian group. So that means I need to have all the group property from the group before. Under addition, the first LLC. About the second LLC, I don't require that much. I just need the second LLC to be associative, commutative in our case, because we consider commutative ring, and has an identity. In this case, we'll call it a multiplicative identity. To differentiate between additive identity and the multiplicative identity, 0 and 1, right? We call it 1 for multiplication. And the third idea is how these two LLC compose together. So the distribution law must hold. Distributivity laws. Okay. Yeah. If you know that all non-zero elements are invertible, so if that means the ring form a group, if you throw away the additive identity, then this ring is what we call a field. Okay, it's what we call a field. So example of field is like the rational number. Let me finish first. So the example of field is rational number, real number, complex number, for example. Yeah, why?
The field have the non-zero ring property.
Non-zero ring property. Oh, you mean so you want to make sure. So you want to make sure that 1 not equal to 0. Yeah. Yeah, usually we don't discuss a zero ring when we talk about field. Yeah. Okay. Okay, let's go on. So this is the definition. Okay. So when we talk about this definition, make sure you have some example in your mind. Okay, next. So after groups and ring, after groups and ring, what do we have? So for a set, right, you must have a subset. You can form subset. But what sort of subset are interesting? So in groups, we can consider subgroups. So what are subgroups? So these are a subset of a group that satisfies a group axiom. Okay. How about subrings? Subrings are also a subset of a ring that, let's call it R. Let's call it R. That satisfies a ring axiom. And you must have the identity from the ring. Okay. You must have the same multiplicative identity from the ring. Then we encounter some concept of normal subgroups. Okay, so when is a group normal? So subgroup N is normal in G, right? In your assignment 3, you learned that if I change G, the subgroup might not be normal anymore. So it's crucial to say that where is this subgroup normal in? So if it is normal in G, if you conjugate all the elements in N, it will still lie back in N, okay, for all G. And then what's the property of normal subgroup? So first of all, a normal subgroup forms a subgroup. Okay, although I say that I claim that this is a subgroup, actually you should show it. Why is it a subgroup? Using the property, the conjugation property here. And there's quite important things. Okay, maybe we'll talk about it later. So this normal subgroup is special. So in the counterpart of rings, you will have ideal. Okay, so what about ideal? So an ideal I is a subset of R such that, first of all, it is closed under addition. Okay, and second of all, it is closed under multiplication. Not just multiplication within R itself, but all ring element. Okay. However, an ideal is in general not a subring. because the multiplicative identity might not be in our ideal. Okay. So why I introduce them together? Because we have a slogan or a fact. So every kernel of group homomorphism is a normal subgroup. And every kernel of a ring homomorphism is an ideal. Okay, so let's recall what is the group homomorphism and ring homomorphism is. So what is group homomorphism? So it is a map phi from G to G prime, right? Such that phi of x plus y equals to phi x plus phi y for all xy in G. So this means that our phi preserve addition. How about ring homomorphism? Ring homomorphism is also a map from a ring to the other ring. And first of all, we have to preserve the additive structure of the ring. It also have to preserve the multiplicative structure of the ring. Okay. And lastly, we have to impose that it sends the multiplicative identity to multiplicative identity. Okay. Okay. And you can check that every kernel of phi is a normal subgroup. And every kernel of a group homomorphism is a normal subgroup. And every kernel of a ring homomorphism is an ideal. Okay. So if a group, it is a group exercise if you don't know how to show. Right. Show that kernel of phi, kernel of group homomorphism is normal and it is a subgroup. And also show that kernel of a ring homomorphism is an ideal. Okay. Okay, let's continue first. So maybe since we talk about kernel of phi, maybe let's go forward to first isomorphism first. First isomorphism theorem. Okay. So before we do that, we need to introduce quotient group and quotient ring. So what are these? So before we do that, we should introduce the key player here. So what's the key player here? So it is the coset. So for groups, we have coset. What are coset? So coset are defined on a subgroup H of G. So what's a coset is? So it is the set where we call AH, such that the element in AH is just you take A, multiply with every element in the subgroup H. Okay, AH like this. So a coset here in general is not a subgroup. So in general, this is not a subgroup. unless A is the identity. Okay. On the other hand, we have a natural choice of yeah. So we want to form quotient ring, right? So we need to have some normal subgroup or normal additive subgroup. So there's a natural choice here. So here, an ideal is automatically and a normal additive subgroup. Why? Because our ring is a commutative ring. Every ring, not just commutative ring, because every ring has a abelian additive structure. So that means it is a abelian group. Inside abelian group, every subgroup is normal. Okay, so in this case here, we have a normal subgroup candidate for rings. Then we can start and form a quotient group, the quotient group and quotient ring. So what's a quotient group? So to form quotient group, this is nothing but just a set of coset. So if I want to take coset, it's important to tell me what normal subgroup it takes. I take a special one, which is the normal subgroup N. So my normal subgroup N must be, my subgroup N must be normal. Okay, otherwise I don't have a group structure. We need it to be normal so that we can commute, right? Can commute, and Bn equals to NB. Okay, Bn equals to NB. In a quotient ring, what do we have? We really do the similar things here. Okay, a quotient ring is a set of additive coset of the normal additive subgroup I. Okay, we form these quotient group and rings. So it is hard to work with these coset because you need to write down the equivalent classes. So we have first isomorphism come to help, where we should just identify quotient group and quotient rings to some ordinary groups and ring that we know. Okay, so both of them are also called the isomorphism theorem. So what's the content of the first isomorphism theorem of group? So always you start with surjective homomorphism. Okay, phi from G to G prime. This is surjective. What you can do is because this is a surjective homomorphism, you can consider the kernel of phi. Okay, and then kernel of phi is normal. Okay, we also have a question later. I will come back to it. So kernel of phi is normal, so you can take the coset of kernel of phi. And the real meat of this isomorphism theorem, first isomorphism theorem, is this quotient group is isomorphic to the image of phi. Okay, it's isomorphic to the image of phi, which is G prime in this case. And there's a commutative diagram to form here. to go from G to G quotient by kernel of phi, I can take the canonical map part. Canonical map, which I send every elements to its coset. And maybe you wonder, how about the isomorphism? Actually, I do the same thing. I send it to A as well, sending the coset to the representative. And then the content here is to show that these things are well defined. Okay. So similar in the ring case, you start with a surjective homomorphism. You start with a surjective homomorphism, and then you take the additive coset of your domain ring. Okay, kernel phi is an ideal, and the ideal in our ring is a normal subgroup under addition. So I can take the quotient as how I do it in the group sense. And then what? And then similarly, I have isomorphism with my image of phi. And then I also have a commutative diagram here where I have a canonical map again from R to R mod kernel phi. And actually the interesting structure here is this quotient ring not only have the structure of group, it also have a structure of rings. So we still live in the rings world. Okay, so I take a ring quotient out by an ideal, I'm still a ring. Okay, these coset have a ring structure, so we are still living in a ring world. So the so the important thing about this first isomorphism theorem is you can deduce that actually every normal subgroup is the kernel of its canonical map. And every ideal is the kernel of its canonical map. Previously, we know that every kernel of a group homomorphism is a normal subgroup. And now we establish that every normal subgroup is the kernel of some homomorphism, which is the canonical map, similarly to ideal. Okay. Any question up to first isomorphism theorem? Wenzuo say for the ring homomorphism is the image of a subring is still a subring. Yes, right. Because I have this condition here. So the image must contain the multiplicative identity. And then the other close condition should be the similar to how you show the image of group homomorphism is a subgroup. Also, oh, okay. Yeah. Yeah, because I still have something to say, but is it better to take a break here and then we resume if there's no question? Maybe let's take a 10-minute break and then we'll resume from first isomorphism theorem, 15.1.16. Okay, let's resume. So let's resume with Li Kai question here. So Li Kai asks, how do you see that every normal subgroup is a kernel of its canonical map, and every ideal is the kernel of its canonical map? So this is simple. You just take phi to be pi in the first isomorphism theorem, and then you pick your G prime simply to be your G quotient by kernel phi. And you ask what's the kernel of this map? In fact, this kernel here, this kernel of this map here must be the kernel of phi. And then you have an isomorphism here. But in fact, this is equal. Okay. Similarly, on the ring side, you have phi again taken to be the canonical map from R, mapping to R over kernel of phi. But what's the kernel of this map here? It should be a kernel of phi again. Okay or not? Li Kai, did you hear me? Are you happy with the answer or not? Or do you have question? Are you okay with the solution I gave?
So sir,
Mm.
so you see the every normal subgroup is the kernel of the canonic map.
Mm-hmm.
So the canonic map is not a isomorphism. Okay, so I mean how to prove every normal subgroup is a kernel. Every normal subgroup.
Okay. I think I get what's your problem is. Okay. I think I did something stupid here. So okay. So okay, let's give a name. Okay, let's give a name. So let's call the name the normal subgroup N. Okay, and then call every ideal I. Okay, so I shouldn't start with G mod kernel of phi. I already tell you the answer. So I should start with G mod N. And then R mod I here. So the question is, what's the kernel of the map from G to G mod N? Really, the kernel here is G over N. Sorry, the kernel of phi is N. So kernel of pi is N. And then if you have a canonical map from the ring to the ring mod I, what's the kernel of this canonical map? What are the things you get sent to the identity coset? It is precisely all the represented the additive identity representative, right? Everything in you send to the identity coset, right? Like this. Does it make sense or not, Li Kai?
Oh, yeah. I got it.
Okay, yeah.
Okay.
Yeah, so when you consider the canonical map, so what are the things that get sent to the identity coset? It is precisely the thing that you caution on. Okay, let's continue. So what type of subgroup ideal example you have? So the easy way to form a subgroup is called the cyclic subgroup. So what's a cyclic subgroup? So you just fix an element A in G, okay? And then you take multiple products of A. Not that the the identity element is in there, because you could take A to the 0. On the other hand, you will have a principal ideal. So what's a principal ideal? You also fix an element in R, okay? And this set consists of the multiple of A by the elements in the ring. Okay, so this is the difference between cyclic subgroup and a principal ideal. And you can actually see that principal ideal is also a cyclic subgroup under additive LLC. So any property about these elements here, these objects here. So every cyclic subgroup is abelian. First of all. Second of all, every subgroup of Z is cyclic. Remember that we proved this using division with the remainder. And typically this subgroup is generated by by the GCD of all non-zero element. Okay, and we have a similar story in the ring case. So what is the principal ideal domain here? So the every ideal of fx, where f is a field, is principal. Okay. We also use the same technique to prove here. So we use division with remainder. And what is it generated by? This is generated by the unique monic polynomial of the smallest degree. Smallest positive degree. Okay, smallest positive degree. Okay, there's a question here. When we check an ideal, is it enough to check Rx in I? Can you give an example that we should also check the additive closure? No, it is not enough to check Rx in I. If it is enough, then I can remove the closure in closure in addition in the definition of ideal. Can you give an example that we should also check the additive closure? Yeah, definitely. So I mean, you can consider the ideal generated by 3 and x in Rx in about Zx, right? You cannot just consider R3 or X, right? You need to check 3 plus X as well, where Rx is in Zx. But seems like this doesn't answer your question. Let me think. Yeah, I think this will be enough to answer your question. You mean is whether 3 plus x is equals to sum r times 3 or 3x plus 3 is equals to sum x times x. I think you cannot solve this. You cannot solve r and x in Zx. So you cannot check closure in addition using closure in multiplication. Okay, yeah. Typically, these two definition won't coincide. That's why we have to list both closure, additive closure, and multiplicative closure for ideal. Okay. Yeah. So let's continue my agenda. So we talk about cyclic subgroup, principal subgroup, and one of the main theorem we encounter is what we call the correspondence theorem. We have both correspondence theorem for groups and rings. Okay, but both of them start with the same condition. So still, we want to deal with a surjective homomorphism. Why do we like to deal with surjective homomorphism? Yeah. Because if you have any map, you can consider just the image of the map. And then your map will be subject onto the image of the map, right? So we have shown that the image of a homomorphism will be a group again, or will be a ring again. So that's why it's suffice to study surjective homomorphism. Okay, so what's the content of the correspondence theorem here? So the content here is, let's say we talk about group first. So we can study all the subgroup in the core domain, okay, using the subgroup inside the domain, okay? And the correspondence here is the subgroup in the core domain correspond to the subgroup in the domain who contains the kernel of phi, right? This makes sense. Why? Because every subgroup contains the identity. And what's the inverse image of the identity? It's exactly the kernel of the homomorphism. And we have a bijective correspondent here. And correspondent theorem for group has more things to say. So H is a normal subgroup of G if and only if H prime is a normal subgroup of G prime. So the normality of a subgroup can be determined either on the right or on the left, depend on which group is easier to study. Okay. And we know more. We know about the cardinality of the group. So the subgroup in the domain has the cardinality equals to the cardinality of the correspondent H prime times with the cardinality of kernel of phi. This is clear once you draw the picture out, which I draw it in my lecture notes. You can have a look. And you can see that actually this is a multiplicative relationship between them. So similarly, in the correspondent theorems in rings, what happened here? In rings, we typically study the ideal. Okay, so the ideal in the codomain will have a bijective correspondent to the ideal in the domain who contain what? The kernel of phi. And one very nice operation you can take here is if you have such bijective correspondent of ideal, what you can do is I can quotient my domain ring with I can quotient my codomain ring with the corresponding I prime, and these two rings are actually isomorphic. Okay, these two rings are isomorphic. And you have seen this being using in the assignment, for example. Any question on this correspondent theorems or not? Maybe this theorem is a bit quite big, so maybe you have some question. Any question on this correspondent theorem? I remember Ming Xiu got some question on this thing, right?
Yeah.
Are you okay with the statement or not?
For the ring one, right?
Mm-hmm.
For the last bijection, can you say that again?
Which bijection? You mean
The
this isomorphism?
Yeah, the isomorphism.
This, this isomorphism. Do you want me to give you the map or?
So you're talking
Yeah.
about two quotient rings being isomorphic, right?
Yes.
Yeah, maybe try giving me the map instead.
Yeah. Okay. So why is it isomorphic? So whenever we talk about isomorphism, right, you need to produce the map, the morphism, okay, which is invertible, right? Isomorphic, injective and bijective. So you need to produce this map here. So what map you should look at? Actually, this is a application of first isomorphism theorem. So you should consider a map from R to R prime mod I prime. What's this map here? This map here should be the composition of map. I know how to map from R to R prime using phi, and how to map from R prime to R prime over I prime. This is what? This is the canonical map. Okay, so the claim here is the kernel of this composition, you have to show it is actually I. So in this case, this composition here form a surjective map. And then once you show that the kernel of this composition is I, you can use the first isomorphism theorem to see the isomorphism between R mod I and R prime mod I prime. So the non-trivial thing is to see that the kernel of this composition is indeed I. Which is not too hard to see, right? Because how do you get I prime actually? What's the bijective correspondence here? Actually, I prime is equals to phi I. Right. And then you are quotient out by I prime. So you are sending the image to 0 here. And then the claim is everything that sends to 0 actually coming from I. Which is not too hard to see. Does it make sense or not, Mingxiu?
Let me digest.
Do you get what everything I say? Do you like know what am I talking about before checking them?
Yeah, I understand the idea, but I need to digest a bit.
Okay. You need to get the statement right first before you check, because otherwise you might checking the wrong stuff. And then you make yourself even more confused. Okay, is it okay? We proceed.
So, sir,
Yeah.
so both of the correspondence theorem actually the important is tell us about the tell us about the cardinality of the subgroup, and then also the and then also the property that it implies.
Yes. So meaning correspondence here. What are corresponding here? These are for groups, subgroups are correspondent to each other. For rings, ideal are correspondent to each other. Maybe one of the rings, the ideal is hard to study, but we know how to study the ideals of the other ring. Then we can use this correspondent to relate the two, right? Does it make sense? Does it make sense or not? Why?
Yes.
Yeah. Okay. Let's continue. Okay. Afterwards, we after these things, what we have are product groups. And product rings. Okay. So actually they are easy as a set because these are just a Cartesian product of a group. This should be as what you have thought. As set, right? Okay, so you just take tuples of group elements. Similarly for rings, these are just tuples of ring elements from two different rings. Might be the same. Okay. And since these are groups or ring, right? So I need to tell you what are the LLC that we define on them. So the LLC defined on them is simple. It is just composing component wise. Because for groups, for the two groups, you know how to act, right? So if you want to combine two tuples together, you just combine component wise. First coordinate compose with the first coordinate. Second coordinate compose with the second coordinate. There's no interference with different coordinates here. Okay, so this is what we call product groups. Similarly, in product rings, for the two LLC, for the both LLC, we will also compose component-wise. It is easy to see that you have to show, okay? This really satisfies the definition of LLC. They are associative, commutative, distributive, commutative if you need, and so on. Just based on the LLC of the original group or ring. So it will be clear if you tell me what's the identity in the product group. Okay, so the identity in the product group is simply the identity in GI, comma, the identity of G2. How about the additive identity in the product rings? Right. So the additive identity of the product rings is simply the additive identity in R1 and the additive identity in R2. How about multiplicative identity? It is again the multiplicative identity in R1 and the multiplicative identity in R2. This is due to the LLC we put on them because we compose component-wise. Okay, when is a group isomorphic to a product group? So remember that this map is given by hash k going to hash comma k going to hash k. If and only if, three cases, hash intersect k is the identity, hash k is exactly G, and one more thing is we require hash k is a normal subgroup of G. So you can split a group into products of normal subgroup if the other condition hold. Okay. How about rings? When can we split a rings? So in rings, we need a help from a specific element called the idempotent, which is E. Okay. And idempotent in a ring is an element such that E square back to itself. Okay. You can think of it as a projection in your linear algebra. So if you project down, if you do an orthogonal projection down into a subspace, and then you project again, you still get the same vector, right? E squared equals to E. So you're doing the same thing if you do twice. So how do we use this? We can actually split our ring into E times R cross with 1 minus E times R. So R goes to ER, comma 1 minus E R. Okay. So these two are rings, but not subring of R. Is it okay with this product groups and rings? Okay, if that's okay, then we go to the last thing I prepare is this group is the group presentation versus the adjoining elements in a ring. Okay, so what's a group presentation? So we say that G is equals to some free group generated by Gi, comma G2 up to Gn, and quotient by some relation. Okay, so this Gi is what we call generators. And this R is what we call relations. So when do we say that these two things are equal? If G is isomorphic to the quotient of the free group generated by the words Gi up to Gn, G1 up to Gn, quotient by the smallest normal subgroup generated by R1 up to Rk. Okay. And what about the adjoining elements? So what's the ingredient we need here? So first of all, we start with a ring. And then we have a monic polynomial. Of positive degree, maybe say n, with coefficient in R. So meaning what? Meaning this guy is in the polynomial ring Rx over R, right? Polynomial ring over R. And we have a root for it. Call it alpha. Then what? Then R join X quotient by the ideal generated by Fx is isomorphic to R adjoin the root. Okay, so in this case here, please take note about this monic polynomial. If it is not monic, something might go wrong. Okay. Yeah, this is the comparison I prepared. Any question or anything you think I missed out that you want to talk about? You want me to talk about?
Sir.
Yeah, so yep.
I want to ask something about the isomorphism. So
Yeah.
isomorphism is a injective homomorphism, but sometimes we can only show the two groups of rings are isomorphic to each other. But what does isomorphic really implies? So we cannot show they are equal, but if we already show they are isomorphic, we take them as like equal. So I want to know what isomorphic really means.
Okay.
Yeah.
Okay. They are not equal. Usually they are not equal. So let's take the example of a ring. Let's take an example of ring. So let's look at this ring here. Okay, we know that these two are isomorphic, right? But they are not equal. Why? Why they are not equal? Because first of all, they are different in terms of elements. First of all, so what do I mean by that? So what's the isomorphism here? Actually, we send x to I. So from here, we can't quite see what's the how to say, What's the difference here? What is x? What is x here? X here actually equals to x plus x squared plus 1 as well. Right. Because it is in the coset. X is in the coset of x. Okay, maybe a bit weird saying that, but what I'm trying to show you is x is an element of x plus the coset of x squared plus 1. And what is the ring structure in this quotient ring here? Remember how we define this quotient ring? This is what? This is the set of additive coset of the ideal x squared generated by x squared plus 1. Because the ideal generated by x squared plus 1 is normal. So we can take the additive coset here. So what are the elements here actually? What are the elements here? There are quite a few elements here, right? So you could have the ideal generated by x squared plus 1. And you have all sort of constant polynomial plus x squared plus 1. And you also have degree 1 polynomial plus x squared plus 1. Right. And what else do you have? You also have all the general degree 1 polynomials, so I think it's better I keep it here together. Right. And these are true for all A, B in R. So by a theory of quotient ring, these guys have a ring structure. So meaning you can add two different cosets together, or you can multiply two different cosets together. But here, what do you have? What do you have here? Here you have, for example, 0, all the real numbers, right? Or all the real numbers times I plus B, like this. So being isomorphic means if I multiply two such things here, so okay, wait. So let's build a bridge between them. So how are these correspond to each other? So the coset of A will get sent to the constant polynomial in Ri, and the coset of Ax plus B will get sent to the polynomial of Ai plus B. So if I multiply two cosets here together, it's equivalent to I multiply two cosets here together. So what do I mean by that? So I could do multiplication in R in the quotient ring first. And I can do multiplication in the R adjoint I. So in the other case, it's easier, right? We can just use the arithmetic to get A squared I plus AB. How about on the other side? We can multiply these guys out. So A times AX plus B plus A times the ideal. And then the ideal times AX plus B plus the two ideal multiplied together. So I mean I'm a bit I'm a bit tricky here because I'm doing a set operation, but it seems like I'm doing the element multiplication. So there's something really to check here, but should be easy to see. This equality should be a set equality. So because you are ideal, right? Ideal multiplied by any elements, you are the same ideal. Okay. So in the end, you really get a square x plus ab plus the ideal s squared plus 1. But under the isomorphism, these two elements get mapped to each other. So this is what I mean by they are isomorphic, but they are not equal. You can see that the operation we did on the quotient ring is really the coset operation. But on the adjoint root polynomial, we only did based on the algebra we have. Does it make sense or not, Sony?
Yes. So basically the operations are similar in the two isomorphic rings.
Yes, yes. Because isomorphic means yeah, they multiply the same way. Yeah.
And
then you can see multiplication in one rings the same in the other ring.
Okay. And about the division with remainder.
Division, yeah.
Yeah. If we have a monic polynomial, we can do division with remainder.
Yep.
But if it is not monic, can still do division, but the remainder is not necessarily the degree less than or equal to n minus 1, right? I mean, just like
Then it loses the purpose of doing division with remainder.
oh, okay.
If you don't reduce the degree, then you can't do much thing. You remember that always we get the contradiction by reducing the degree.
Yeah.
If we don't reduce the degree, maybe you couldn't get most of the contradiction.
Okay.
That's why we want a monic polynomial.
Okay, thank you, sir.
Yep. Yeah, any other questions? Or do you want to go through assignments? Can you continue for I can, but those are not in the exam, so I'm not sure how many of you are interested about integral domain and maximal ideal.
So I think focus on the exam first.
Sure. Yep. So focus of exam. I think there's almost everything I want to say. So maybe we talk about assignment. Okay, I have give you back your assignment for so you can have a look, and if you think that there's some dispute in your mark, you can talk with me. So first question in the assignment 4 asks you to prove that the symmetric group S3 of 3 indexes, this is what we have defined since the first or second class, has at least 2 isomorphic group presentation by generators and relations. And I give you these two presentation. So the point of this question is I want you to build a map, okay, between S3 with these two presentation, and then show that this map is surjective and injective. Okay, most of you cannot show it is injective. Maybe because I speak a bit too quick on the matter, and then you might not get it. But I'm glad that some of you get it and then you write it out in details, because the point I asked you to prove something that I proven in class is to write in details what I say. Okay, so meaning you cannot just argue based on what based on how to say. You cannot just how to say, for everything you don't understand, right? Make sure you make it clear to yourself why is it true. Okay, not because of people telling you why is it true, then it is true. I think this is very important for your life even. Yeah. Otherwise, you will easily get fooled by people. You'll be easily get controlled by people. You understand what I say? So make sure you know everything based on your understanding. Okay, don't build on the others' understanding. All right. So what's the map here? I think most of you get the map right, but just that you cannot show why the two maps are injective. So there are a few ways to show the maps are injective. One is you check that the presentation I show here has all the relation. Okay, you check that these are all the relation that need to satisfy by the generators. Or you show that through these relations, there are only 6 elements, 6 coset, 6 different coset that you can build. Then you have if that's the case, then you have a surjective map on 6 elements. Then it should be surjective. Okay, this is some discrete math argument. If you have a surjective map on finite set, that map must be injective. Okay or not? Does it make sense? So the argument here I gave is I use the cardinality argument to say that I only have 6 coset I can build from the relation. Similarly for the second presentation. Some of you just say by a cardinality argument and then didn't tell me how to reduce all the words in the quotient group, so I cannot give you full marks. Yeah. Any question on this part 1, question 1? Okay, if not, we continue. So question 2 asks about S3 acting on a 2 set of order 3, and then we try to decompose the product set UV into the orbit for the diagonal action. First case is when both operations are transitive, and then second case is transitive on one of them, and then there are 2 orbits for the other 2. So this question is kind of tricky, very tricky, because I didn't tell you what's the group action. I just tells you it acts, and then I tells you that the action is transitive. So you need to kind of guess from here what kind of action it is. So one way you can do is you go and try how transposition should act on a set, right? Because by group action, all the action can be decomposed into the action of generators. But S3, like previous question, tells you that it generates by 2 elements. So you just need to check 2 transposition, for examples. And then you see that when can transposition act the same, when transposition should act differently. Another way to see this is to see through the kernel of group action. So meaning the kernel of the permutation homomorphism. So look at the kernel of phi from G to perm X. So the kernel of this homomorphism should be a subgroup of G, which is normal. And there are only 3 normal subgroups in S3. You can check, which is the identity subgroup, the whole group, and then the alternating group, which is the group of even permutation. So if you have the kernel to be the whole group, then surely your action can't be transitive because you send every element to itself. Okay. So the only case you have is the identity subgroup as a kernel, or the group of even permutation, which is the alternating subgroup as a kernel. So if you play long enough with these two things, you can see that when your kernel is the trivial subgroup, 2 transposition must act differently. Okay. And then if your kernel is A3, then all the transposition must add the same. Okay. Since they add the same, we can do some relabeling so that it add on V2 is sending V2 to V3, so that we have an orbit of V2 to be V2 and V3. Right, so this is the strategy we use. So up to relabeling, we can just send ui to u sigma I. So meaning if I label the 3 elements in my set, ui, u2, u3, vi, v2, v3, if I want to add a transposition on them, I'm just transposing the indexes. Okay. And then from here you can find the orbit. So for the first case, it splits into 2 orbits. So first orbit is when I equals to j. Okay. So this case is like u1, v1, u2, v2, u3, and v3. The other case is for I and j are different. Okay, they form an orbit. For the second case, it also split into 2 orbits. So the first orbit is you have v1 fixed and then u1 changing. Okay, and the second orbit is ui vj such that j not equals to 1. Okay, so both cases you split into 2 orbits. Yeah, any question on this question 2 you want to ask? Okay, continue. So question 3, given a group action G on X, we can obtain a permutation representation as we discussed just now, and vice versa. Prove that these 2 definitions of faithful group action are equivalent. So first is that permutation representation is injective. Second is Gx equals to X for all X if and only if G equals to identity. I think most of you did pretty well on this question. Just that when you show for the second statement here is the if and only if statement. You miss most of you miss the direction from the right to left. Although this direction is trivial, but from logic wise, you need to prove 2 direction here. Yeah. So this from right to left actually trivial, because if you take G equals to E, Ex always equals to X by a group action. So a lot of you miss this one. Okay, which I penalize a bit. In general, it's okay. Anyone got problem understanding this question 3 or not? Or you have different solution? Okay, if not, let's go on. So question 4 is a upgrade of this question 3. So suppose Gx on the set X and phi is the associated homomorphism from G to perm X, which is the permutation representation. Show that G mod nx faithfully if and only if n equals to phi. Okay. So in the class I show that if G mod nx on X, then n is a subset of curve phi. So I help you solve half of this question. So this question split into 2 parts. So one part you have action and faithful, the other part you have 2 inclusion. So one inclusion corresponds to action, one inclusion corresponds to faithful. Some of you just copy the solution in my lecture notes, but the lecture notes is just deal with action. It doesn't deal with faithful. So there's another word, another word you need to do for faithful. Okay. So first suppose that phi is injective, and you want to show that kernel of phi is in fact the subset of n. So let G be in the kernel of phi, that is Gx equal to X for all X in X. Consider the action of Gn on X. And you will see that Gn on X is defined to be G on X. But G is in the kernel of phi, so G must be in X. So since this holds for all X, we see that Gn is in the kernel of capital phi here. So this capital phi here is different for the little phi. This capital phi is defined to be the permutation representation for G mod n. So since this capital phi is injective, so what's the identity in G mod n? So the identity of G mod n is n. So meaning Gn have to be equals to n. So by the TFAE statement we have before, or you show it that G have to be in n. How about the other case? Suppose that kernel of phi is a subset of n. And we want to show that the capital phi is injective, meaning you suppose phi gn equal to phi hn. Okay, so this is capital. I should change this. It follows from the axiom of group action what? Phi of h inverse gn should be the identity. In other words, h inverse gn composed with x is always x. Using the definition of the induced action, this is equivalent to what? Equivalent to the statement that f inverse g composed with x is always x. So here there's a spacing, which in turn implies that h inverse g is in the kernel of little phi. Okay, meaning what? We already suppose that kernel of phi is a subset of n. So meaning h inverse g should be that element of n as well. So by the TFAE we have before, this implies that Gn equals to Hn. So we have proved the injectivity. Because we have phi Gn equal to phi Hn implies Gn equals to Hn. Okay. Is it okay with this question here? Question 4. Okay, if that's okay, we look at question 5. Question 5 asks you to show structure whether the following set are rings or not. Most of you did pretty well. For 5A, you could either use a Venn diagram to show the associativity, commutativity, and so on, or you can use the algebra of set theory to show it. Both of them are okay. And B, some of you miss B. So B is a set of continuous functions from R to R. The addition is defined by addition pointwise, but the multiplication is defined to be a composition. Okay, so most of you realize that composition is not commutative and then you give a counterexample. But a lot of you miss that actually distributivity doesn't hold as well. Okay, distributivity doesn't hold in this case as well. A ring under the LLC. Okay or not? Doesn't form a ring under the 2 LLC. But a continuous function might form a ring under multiplication point-wise and addition point-wise. You can try and show it. So this is a question assignment 4. Any question about assignment 4 in general? I've posted out the solution on Moodle. You can download it and read together. If not, we go on to assignment 5. So I haven't complete marking your assignment 5, but you can read the solution and then compare with your own solution, see what you have left or what I written for my solution. Okay, so for assignment 5, question 1. So find generators for the kernel of the following map. So for part A, what do? We substitute x equals 0 and y equals 0. So this is like the substitution principle. So what's the kernel here? So the kernel here consists of all polynomials with the property that each monomial summand has degree at least 1 in either x or in y. So if you want to prove it formally, you can use division with remainder, where you divide the polynomial in the kernel with x first, and then you found that the remainder is everything in the power of y, and then you can divide by y again. Okay, so division with remainder works with a polynomial ring of multi-variables. Okay, part B. So it's again substitution principle. You sub x to square root 2 plus square root 3. And then you try and find what's the polynomial in zx that has this elements as a root. So some of you ask me how I come up with x to the power 4 minus 10 to the power x to the power 2 plus 1. How do we come out of this? Yes, you have to try and error. So you have to multiply with some conjugate. Because first you need to think about how you make this radical into a non-radical number. So you need to make full use of the conjugation. Okay, it's like how you make complex number into a real number. So you try out that actually you need 4 of them. Okay, you need 4 of them. So you need to show that y x to the power 4 minus 10 x to the power 2 plus 1 generates the kernels. So formally also you would use the division by algorithm, division with remainder. So to see that we can't find a polynomial of the lower degree with square root 2 plus square root 3 as a root, so we check that x minus square root 2 minus square root 3 square and x minus square root 2 minus square root 3 cube have a summand of square root 6 and x times square root 6 respectively, which cannot be cancelled by adding lower order terms because the coefficients stay in a different ring. Part C. So part C, you have also substitute principle. We substitute x to t, y to t squared, z to t cube. And then you check that you only need 2 polynomials to generate your kernels, which is you can take y minus x squared, z equals z minus s cube. I briefly discussed this in the class where I expressed the third generators of the kernels using the other 2 generators, so we only really need 2. So how to show that this 2 works? Similarly, you will use division by remainder. So if you first divide by x minus s squared, then you will left your polynomial with everything in x and z. And then you divide again px comma z with z minus s cube. and then you will turn everything in term of everything just in term of x. And then you can check that you cannot have non-zero coefficient on the monomial of x. Otherwise, it can't exist inside your kernel. Okay, so this is for the first question. Any question or not? Okay, if not, let's go to the second question. So second question asks you to identify the following rings. So these are all quotient rings. So you take quotient of zx by some ideal. Okay, so how to do this question here? So usually the technique to do this question is we have done in class. So what we do is we try to play around with the generators in the ideal. See if we can find some simpler generators or not, like integer, so that we can quotient the rings, the polynomial rings with these integer generators first. Because we have seen in class that if your ideal is generated by multiple generators, we can quotient in different order. So we can reduce the size of our polynomial ring first by reducing the size of our coefficient. And then we can start quotient by the irreducible polynomial or the monic polynomial. Okay. Yeah, so in the first example here, you can show that actually 2 lies inside this ideal here. Okay, so meaning what? Meaning we have 2, by quotienting out x squared, the ideal generated by x squared minus 3 and 2x plus 4 is equal to the ideal generated by x squared minus 3, 2x plus 4, comma 2. So you can quotient by 2 first. So I reduce my coefficient to z mod 2 first. If I do this, 2x plus 4 is immediately get sent to 0. Okay, and then I have impact on x squared minus 3 as well. So you need to consider minus 3 under z mod 2, which is x squared plus 1, which is 1. So in this case here, what is x squared plus 1 here? So this is equivalent to adjoining the square root of minus 1. Okay. Note that in this question, right, this root is minus 1, right? But you cannot really just say that this ring is z mod 2z. Because why? Because minus 1 is the root of x plus 1. Okay, so in fact, z mod 2z is isomorphic to z mod 2z x quotient by x plus 1. Okay, so this is a comment I want to make. So be careful when you want to adjoin roots. Okay. Okay. For part B. So for part B, the answer is z mod 3z. Why? Because you can show that the ideal generated by 6 and 2x minus 1 is actually the ideal generated by 3 and x plus 1. Okay, so you can mod out the ring by 3 first, and then you use root adjoin minus 1. So in this case here, it's really minus 1. So you will reduce to z mod 3z. So this is the case I mentioned just now, similar case. For part C, similarly, so part C, because of my typo here, so there are two solutions here. So if you do the question that quotient out by 2x minus 4 and 4x minus 5, you will get z mod 3z. If you do the example, the textbook example, 2x squared minus 4 and 4x minus 5, you will get z mod 7z. So the technique is the same. So see whether you can find the generators which is simpler to do quotient, and then you continue from there. Okay, it's a similar story repeated. Substituting. Okay, and for the last question here, you can see that 5 is in your ideal. Okay, so you can mod out by 5 first, and then you realize that you cannot split x squared plus 3 further, so you need to adjoin the root for x squared plus 3. But plus 3 in mod 5 is minus 2, so it satisfies alpha square equals to 2. So this is for question 2. Just feel free to stop me if you like. So let's continue. Question 3. So let R be a ring, and let I be an ideal of the polynomial ring, and let n be the lowest degree among the non-zero elements and of I. So prove and disprove the following. I contains a monic polynomial of degree n if and only if it is a principal ideal. Okay. So one direction is true and the other direction is false. So which direction is true? So if I contains a monic polynomial of degree n, then it will be a principal ideal. This is proven just using the division with remainder. The other direction, you can consider a principal ideal generated by 2x in zx. Okay. Since 2 is not unique in z, so we cannot reduce this 2x to x inside my ideal. So you won't find x inside the ideal generated by zx. So we have shown that if it is an principal ideal, it might not contain a monic polynomial of degree n. So this is for part 3. Okay, how about part 4? Question 4. So question 4 here's first part, prove that the intersection I intersect J is an ideal. So this is a standard question, like how you show intersection of a subgroup with a subgroup. And B, show that by example, the set of product XY need not be the subgroup, need not be an ideal, but that the set of finite sums xi, yi, or sv, yv of products of elements I and j is an ideal. This ideal is called an product ideal. So this part B tells you that it's not enough to just consider the product from two ideals. You need to take the sum of them. So this is kind of similar to what Ziqian asked just now. Is it enough to just check the product closure and the product or not? No, you need to check the additive closure as well. So you need to take the additive, the addition between the elements in the set. So the example I have here is the ideal generated by x and y and the ideal generated by x squared and y squared. Why? Because if you consider xy squared and yx squared, which is equals to xy times y plus x, it is not a product of an element in I times with a product with elements in J. Okay, although it is a sum of such term. Okay, yeah, to show is an ideal is kind of standard. And last part is to say about the relation between ij and I intersect j. So one can see that ij is a subset of I intersect j. Okay, and then the other direction is not true because we have part B telling you that the other direction is not true. Okay. Yeah. So let's continue. So last question is about whether two rings are isomorphic or not. So these two rings are not isomorphic. So we will prove this by contradiction. How I prove this is you can consider you can first suppose there's an isomorphism between these two rings. And what I do is you need to show that there's a square root in zx over x squared plus 7 for minus 7. But you need to show that there's no square root of minus 7 in the in the quotient ring of zx quotient by 2x squared plus 7. Or there's a more easier, not easier, but easy to see way is you can use correspondence theorem, right? So suppose you have isomorphism between the two quotient ring. Okay, you can use correspondence theorems to play around with the isomorphism. So what you can do is you take the ideal generated by 2 in both cases here. So they are in a bijective correspondence. Okay. And then what you do is by the correspondence theorems says that I can, for the both ring, I can quotient by the two corresponded ideal. But as you can see here, on one side, what do you get? You get z mod 2zx quotient by x squared plus 7. 7 quotient by 2, you get 1. And what is this? This is what we have done just now is z over 2z adjoint I. But what about the other side here? You have z mod 2z x quotient by 1. Because 2x squared is 0, 7 quotient 2 is 1. So if you quotient by 1, what does it mean? 1 is a unique ideal, meaning this is the whole ring. So you quotient out everything, what do you get? You get 0. So these two shouldn't be isomorphic. So this is the other way, if you like. So this conclude the assignment 4 and 5. Any other question before we dismiss? Why is adjoining the root necessary? Why not just leave it as a quotient? So this go back to the question of Suoning, right? This go back to the question of Suoning just now. Right. Do you prefer to write a lot of code set, or you just remember what happened? What happens to the x? Do you prefer to write all the code set down? Do you prefer to work with code set, or do you prefer to work with just algebra? Right. So this is why it's necessary to adjoin the root. It will make clearer what our quotient must to be, right? Does it make sense or not? It's a convenient way to see the quotient ring instead of writing the additive code set down. Ziqian, do you get me or not? Is Ziqian still there or not? Yeah, okay.
So, sir.
Yeah.
So this time is we focus on the assignment, right? The assignment question.
I don't want you to focus like this, but assignment must is important. The focus is from the correspondence theorem of groups up to the product rings. Yeah. I cannot draw further specification because if you learn part by part, your knowledge will be block by block, so you cannot link everything together. In particular, now I didn't give you the definition, so you will most probably miss some of the definition. So make sure you know how to link all the ideas together. So the most important thing is what I have run through just now. So make sure when I run through this key point here, you have at least some example or exercise. You know how to check, how to manipulate, how to play around. Okay, do you know how to play around with normal subgroup? Do you know how to play around with ideal? Do you know how to play around with quotient group, quotient ring, product groups, product rings? So for all these idea, you need to have at least one example in your mind or one few example that how the question that I asked in the assignment or example in textbook. Yeah. Does it make sense? Does it understand? Do you understand how you should prepare now? Is it clear on how you should prepare? Will I share the note? Yes, I will share the note afterwards. I will share the notes afterwards. Are you clear on how to prepare for the exam? Okay. Any other question? Last question? Who put good? Soning good. Okay, thank you. Others got last question or not? So the abstract algebra test exam is quite early on the first week. So please prepare well. Manage your time well. Don't procrastinate. Because I treat you guys as an adult, so you need to manage your life well. Okay. Don't bring troubles to others' life. Yeah. So if there's no question, then I will see you if we gonna meet again. I mean, at least in the final, but we'll see you in future. Okay. Okay, see you. Okay, bye.